Okay guys, welcome back. So in this video and the videos hereafter I'll be talking about basic thermodynamics. So what is meant by thermodynamics? What is the topic of thermodynamics and what is there in thermodynamics? So that is the concept. Alright. So when you think about a system, right? Now consider that you consider a refrigerator, right? Consider a refrigerator. Now if you give 100 joules of energy to the refrigerator, you know that this energy will not be completely used, right? This energy will not be completely used by the refrigerator to give you cool, right? Give you the heat required. And also for all the other appliances, even a microwave or a stove or anywhere, the total heat given to the total energy given to the system is not used by the system. Some energy is dissipated to the environment. So that is the basis of thermodynamics, sometimes also called the first law of thermodynamics. And the first law of thermodynamics and the other concepts will be described in another video. But for the introduction of thermodynamics, I need to explain it to you. So that is the importance of thermodynamics. Now thermodynamics is important as to know whether when we give some energy to a system, what energy is used by the system and what energy is lost to the system, and how this is lost and how we can minimize it, how we can increase it if we want, right? And the other concepts related to it. So in order to understand basic thermodynamics, there are two components that are important in understanding the energy in the relation of energy to the supplied to a system. Those are the work done by a system and the internal energy of a system. So the work done by the system will be the major topic in this video, and the internal energy of the system will be talked in another video. Alright. So what is the work done by system? Alright. So that I will be discussing in this video. Work done by a gas. Right? Alright. Now I'll take a simple setup. Right? A simple work done by a gas. Work done by a gas. Right? Work done by a gas. So in order to understand what is work done by a gas, so you know that what is the work done in mechanics. Alright. So work done in mechanics is a simple concept in which when we have some object, say a mass m, is actually regardless of the mass, right? Mass is not important. Say a mass object of mass 2 kilograms, and we apply a force of say 20 newtons to this object. And this object, considering there is no friction between the object and the surface, now I'll just draw a simple setup. Otherwise it will be confusing. Okay. This is the system I am talking about. So this is the mass of 2 kilograms. So it's not the mass is not relevant here. So if I give a force of 20 newtons here, some force 20 newtons, right? And considering that there is no friction between this object and the surface, this the total frictional force, so the resultant force will be equal to the applied force, which is 20 newtons. And assuming this object after some time t moves a distance say 5 meters, so the total work done, you know, is the product, right? The dot product or the scalar product, because work is a scalar product of this force times the displacement, which is 20 times 5. So 20 newtons times 5 meters is 100 newton meters, so 100 joules. So the work done is 100 joules. So what is meant by this is that when you give some force to either to a moving object or to an object which is initially at rest, this object moves in this direction and does some work, right? Does some work to this system. Now actually in the case of a gas, what actually happens is that the work done by a gas is done by the gas. We actually supply the heat to the gas, right? And sometimes we don't actually supply the heat. The gas already has some heat on it and it converts into another form of energy. So the work done by a gas is a similar concept. So I'll use a simple setup in order to explain it to you. So if you have some gas like this, if you have some gas and if you have a piston like this, and if I now initially say this is stationary, right? This piston is stationary. And if I give some force F in this direction, this piston moves in this direction, right? Say at distance d, distance d, right? So you can say that the force applied, right? Force, now you know that the pressure is equal to the pressure is defined as the force per unit area. So pressure is equal to force divided by area. Force divided by area, right? So the work done by the system according to normal mechanics we have been learning so far is W equals F times d, the force times the distance, because the force and distance are in the same direction, right? We don't have to decompose that. So the work done is force times the displacement. So what actually happens is that now according to this equation we can say is if the pressure is equal to force divided by area, by cross multiplication you can say force is equal to pressure times the area. So what actually happens is that the work done by the system is pressure times its area, which is the force, and substitute that here, times the distance. So area times the distance, area of this piston times the distance it travelled is the volume it travelled. So I'll take it as delta W, right, a small distance. So that is P times delta W. So delta V, right, delta V. So W equals P times delta V. So W equals P times delta V is the work done by a gas, right? It's a very important relationship in thermodynamics and many other concepts. So W equals P times delta V. So that's the work done by a gas of pressure P and volume when we displace it by a volume of delta V. So work done by a gas is one of the important theories that we have been using. So say that when you give the volume of a gas at some pressure, I'll take the pressure to be 10 to the power 5 pascals, and the gas expands by 0.01 cubic meters, right? So let's take a simple example. So if the pressure supplied to the gas, right, pressure supplied to the gas is 1 times 10 to the power 5 pascals. Pressure of the gas, right, not pressure supplied to the gas, pressure of the gas is 1 times 10 to the power 5 pascals, and the volume expansion is 0.01 cubic meters. So the work done is pressure, which is 1.10 to the power 5 over 10 to the power 5 times delta V. Delta V is the expanded amount, right? The expansion. So the expansion is 0.01 cubic meters. So this has to, for the work to be in joules, we should be also in SI units. So we have already been given in SI units, so we can directly substitute it. So this will be 0.01. So 0.01 times 10 to the power 5. So 0.01 is 1 into 10 to the power minus 2. That into multiplied by 10 to the power minus 5 is 1 into 10 to the power 3, which is 1000. So W equals 1000 joules over 1 kilojoule. 1000 joules or 1 kilojoule. Right? So that's a simple calculation, right? Just to mention you about a simple example, right? That's not a big calculation. There are many calculations that you can do using this equation. It's just a simple calculation in order to explain it to you, right? So that's the work done by a system. So work done by a gas. So work done by a gas is one of the important concepts. And the next concept is the internal energy of a gas, which I will describe in another video. And thanks for watching this video, and see you then.